computational problems, in particular what we call the shortest vector problem. This is going to be the central computational problem that we'll describe. And I'm going to show really the most famous lattice algorithm was ever invented, namely the LLL algorithm, the Lenstra-Lenstra-Lavash algorithm, which computes a relatively short vector. Okay, so that's the goal of this lecture. Let's write this down.
Either way, will you give us some the proof of the generalization or not?
No, I wasn't planning to show it.
So, what do you use to generalization?
So it's essentially the same ideas for that you used to prove Minkowski's theorem, except that it's sort of in a high level, it's a sort of a recursive application of Minkowski's theorem. So once you find bound on lambda 1 of L, you sort of consider the sublattice. So you remove that vector from the lattice, and then you consider sort of the sublattice, and then you kind of sort of recurse on that. So that's roughly speaking the idea, but it's complicated. It has a lot of bookkeeping and everything. But
we can prove this with only with the Minkowski theorem.
So I don't. So it's a good question. So can I use Minkowski's theorem as a? So this is called, by the way, this is called Minkowski's first theorem. Why? Because there is a second theorem. So this is called the Minkowski's second theorem. So I don't know if we can use the first theorem as a black box to prove the second theorem. I think you need to use the techniques within. I'm not completely sure about this. Okay. All right. So what we are going to do is we are going to talk about computational problems on lattices. And really the canonical problem that we will talk about is the shortest vector problem. What I will call SVP, shortest vector problem. And what this, so remember that we showed Minkowski's first theorem, right? So what it says is there exists a relatively short vector in the lattice. But the proof of this theorem is highly non-constructive. It says that there exists a short vector, but doesn't tell you how to find it. Okay? So the shortest vector problem, asks for the following: given a basis B, find a vector in the lattice generated by B, such that the shortest vector in the lattice generated by B. We find the shortest vector. That's it. That's the shortest vector problem. Okay. This is in fact the search version of the shortest vector problem. You can also define an optimization version, which says given a basis B, you don't have to find the shortest vector. Just tell me the length of the shortest vector. Okay. Clearly, if you can find the shortest vector, you can compute its length. So this is an easier problem. Okay. And then there is the decision version of the shortest vector problem, which says given a basis B and a number R, decide if lambda 1 is bigger than R or not. Okay? You don't even have to give me the length of the shortest vector. You just tell me if it's bigger than this number R or not. So this is the decision version of the problem. Okay? And in fact, it turns out that all these problems are equivalent. So if you can solve the search problem, if you can find a vector, you can compute its length. Clearly, if you can compute its length, you can solve the decision problem. But it's also true the other way around. Okay, this is not very hard. It's not trivial, but this is true. I'm not going to tell you.
You mean polynomial equivalent?
Polynomial equivalent, exactly, precisely. So in fact, let me actually tell you a sketch of the proof of this. Right. So if you can solve the decision problem, you can solve the optimization problem. Okay, and this is actually very easy to see. So there's no trickery. Can anyone guess how? Exactly. So binary search. Okay. Right. So if you can tell, if I give you a number and you can tell me if it's bigger than this or smaller than this, I can do binary search on the interval. So I know that I can compute. Okay, so this is the non-trivial part which I didn't tell you. I can compute an exponential approximation to lambda 1. So I can sort of compute a number which is at most exponentially larger than the true lambda 1. And now I have an interval in which the real sort of lambda 1 lies. Now I do binary search, I can figure out the exact value of lambda. Okay? Good. Okay. So for this I use the oracle. So every time I use this oracle to say, is this bigger than this or not? If it's bigger than this, well, I'll divide this interval and then say bigger than this or not, and then keep going. This can also be proven, but it's not quite as straightforward. I won't describe it. Okay, so this is the shortest vector problem, and I will also use the describe the approximate shortest vector problem. It says, shortest vector problem is 5. Okay, it's very hard to compute the shortest vector. Now let me relax the conditions a little bit and say, you don't have to give me the shortest vector, just give me an approximate shortest vector. Give me a vector that is 100 times, at most 100 times as big as the shortest vector. At most, square root n times the shortest vector. 2 to the n times, right? So in particular, gamma shortest vector problem says, given a basis B, find a vector V in L of B such that the length of V is at most gamma times lambda 1. Okay? Gamma is a parameter of the system. It could be 2, 100. If gamma equals 1, it's the exact shortest vector problem, and it becomes easier as gamma increases. Okay, and similarly, you can define sort of approximate variance of the optimization and the decision problem. Okay. That's good for now. The other problem which we won't talk about so much is the closest vector problem. Closest vector problem, which says I give you a lattice and I give you a point in space. The point is not in the lattice necessarily, it's somewhere in space. Find me a lattice point which is the closest lattice point. Okay, so if you have a lattice, right? I give you this point y. Find me the closest, lattice point to it. Okay, so it's given b and y in q to the m, perhaps. Find a v in the lattice such that v minus y is the smallest. So v is the closest lattice point to y. Okay, so we won't talk about the closest vector problem so much. We'll just focus on the shortest vector problem. Again, like I said, the Minkowski's theorem is not constructive. And we don't know how to find the lattice vector which is smaller than this one. All we know, the best thing that we know is, I'm going to keep this and I'm going to erase the rest. The best thing that we know is given by the Lll algorithm. Lll is Lenstra and Lovash. Named for its inventors. And what it shows you is, given a basis B, find a vector V in the lattice such that the length of V is at most, this is an m-dimensional basis, 2 to the m minus 1 over 2 times lambda 1 over 2. Okay, so it doesn't find you the shortest vector. It finds you a vector that is at most a 2 to the m minus 1 over 2 factor bigger than the shortest vector. Okay, so in constant dimensions, if m is a constant, this is actually pretty good, right? If m is 5, you get at most 4 times the length of the shortest vector. But as m increases, things become a lot worse. Okay, so what this says is that the shortest vector problem in small dimensions is actually pretty easy. And the hardness of the problem comes from the fact that there are many dimensions. Okay, this is what we will use in cryptography in tomorrow's lectures. Okay, so this is an algorithm. It was invented in, I think, 1985, maybe 1986, and it has never been improved since. This is really the best, approximation algorithm we know, more or less. I mean, we have improved this by sort of a logarithmic factor in the numerator. So now we know sort of 2 to the m over log m, so to speak. But that's no other substantial improvements to this bound are, no other substantially better algorithms are. Okay. Okay. So the objective of this lecture is to show you this algorithm and sort of analyze its correctness, its running time, and so it shows how to do this in time polynomial in the input length. And this is important. Well, the input length means the description of the basis. So the input is the basis, and how many bits do you need to write down the basis? That's the input length. And okay. So this is what we are going to show. Okay. So before we start describing the algorithm, for this really hard problem, let me actually handle easy problems first. Right. Let me tell you a couple of problems which are easy, given what we described in the first lecture, right? Easy problems. One is membership. Okay, namely, given a basis B and a vector V in Z to the M, decide if V belongs to the lattice. Okay, I give you a basis of a lattice, generates a lattice. I give you a vector, and you tell me if it's in the lattice or not. Okay, so this is the membership problem. Easy, hard. What are the? It's clearly easy, but how do you? Any ideas on how to solve this? No. Okay, so this is actually pretty easy. In fact, you can write any vector as b times x, right? Because v is in the span of b as a vector space, where x is some vector. It's not necessarily an integer vector. So I can actually compute this vector. Now just check if x is an integer vector or not. If it's an integer vector, then v belongs to the lattice. Otherwise, not. That's it. Plain, right? Plain and simple. The second problem is equivalence. Given two bases B1 and B2, check if decide if the lattice generated by B1 is equal to the lattice generated by B2. Okay, easy, hard, and how do you, clearly easy. How do you solve this? Any ideas? Exactly. So in fact, we had a characterization of equivalent bases in the first lecture, which says that the two bases are equivalent if and only if I can write B2 as B1 times a unimodular matrix. So now compute this matrix U and check if it's unimodular. That's it. Okay. So what is my point in describing all these easy problems? Okay. There is a rule of, I don't want to commit to it too much, but there is a rule of thumb which says that problems that are algebraic in nature, okay, which don't talk about norms, which don't talk about sort of the lengths of the vector, small vectors and long vectors and so forth, tend to be easy. This is not a rule set in stone, but that's the way, it's sort of an observation about lattice problems. On the other hand, when you get into a problem that talks about length of a vector and kind of minimizing the length and the norm and so forth, that tends to be hard. Okay, this is not a sort of a 0-1 rule. There are problems that fall into kind of both sides of the spectrum, but it's a good thing to keep in mind. Okay, so those are the easy problems. So now let me show you how the LL algorithm works. Okay, we need to do this. We need. I need to describe what's called the Gram-Schmidt orthogonalization. Well, quite a mouthful. Orthogonalization method. Okay, so this is a very important algorithm which I will use as a kind of subroutine in the LLM algorithm. And what this does is the following: it takes a basis of right? Our favorite basis, so forth, and converts it into an orthogonal basis. Okay. In particular, so let's say this is B1, this is B2. It constructs a basis B1 tilde, B2 tilde, which is orthogonal. B1 tilde and B2 tilde are orthogonal. And this new basis has some very nice properties. Okay, so it's a way to convert a basis into an orthogonal basis. Now, of course, the vectors B1 tilde, B2 tilde, and so forth are called the Gram-Schmidt vectors. Now, clearly, the Gram-Schmidt vectors are not necessarily in the lattice. They are just arbitrary vectors in the real space, and indeed it's not necessary that a lattice has an orthogonal basis. So the lattices don't generally have an orthogonal basis. The only lattices which have orthonormal basis, orthogonal basis, are the integer lattices or shifts of integer lattices or sort of scalings of integer lattices. Okay, so this is not necessarily a basis of a lattice, but it's the basis of sort of the R to the M as a vector space. Okay, so so what is the process of computing the Gram-Schmidt orthogonalization? Well, I will start with the first vector, right? And I'll keep it exactly as it is. So in fact, the first orthogonal vector is equal to B1. And the second orthogonal vector, well, what I'm going to do is I'm going to look at B2, okay? And I'm going to look at, determine the component of B2, which is orthogonal to B1. Okay, so I can write B2 as this guy plus another vector which is in the direction of B1, right? And in fact, this guy, the orthogonal component of B2, is the Gram-Schmidt, is the second Gram-Schmidt vector. Okay, so pictorially that's what it is, but how do you compute it, right? How do you compute it? Well, I'm going to take B2, and I'm going to subtract. I can write B2 as the sum of this and the vector in the direction of B1. So just subtract the this vector in the direction of B1, right? And in fact, this vector in the direction of B1 is a projection of B2 onto the space spanned by B1. So B2 tilde is B2 minus a multiple of B1. Again, what is this multiple? I'm going to project B2 tilde onto B1 tilde, right? And I'm going to scale it appropriately. Okay, B2 in a product with B1 tilde, which is equal to B1, but divided by the length of B1. times B1. Okay? So I'm going to take B2, subtract some multiple of B1 from it. So I'm going to shift it in this direction by some multiple of B1, and that's how I get B2 tilde. Okay? So why is this? Why are B1 tilde and B2 tilde orthogonal? Well, let's compute it, right? Let's compute B2 tilde in a product with B1 tilde, right? This is equal to B2 in a product with B1 tilde. Right? I'm just taking this equation, taking the inner product with B1 tilde on both sides, minus B2 in a product with B1 tilde divided by B1 tilde, the same as here, times the inner product of B1 with B1 tilde. Okay. Now B1 and B1 tilde are the same, so I might as well sort of replace it, put a tilde on top. Okay. Now this is the same as this, gets cancelled off, and this is the same as this, gets cancelled off. Okay. So I get 0. So in fact, it's easier to see this in picture, and doing the algebra actually makes things a bit complicated, but these vectors are orthogonal, at least in 2 dimensions. In fact, you can generalize this to n dimensions, and what happens is that if I want to compute the ith Gram-Schmidt vector, I take the ith basis vector. So this is sort of an iterative process, right? So I compute the first, the second, the third, and so forth. I want to compute the ith. I take the ith basis vector bi. So in 3 dimensions, it's this vector, right? And I compute the projections of this vector to the first and the second Gram-Schmidt vector and subtract it. Okay. So in particular, di tilde is bi minus the sum of a bunch of numbers times dj, where j equals 1 to I minus 1. Right? I'm going to take bi, and I'm going to subtract, shift it by multiples of smaller, I mean the vectors b1 up to bi minus 1. And what is this multiple? It turns out that this multiple is bi in a product with bj tilde divided by bj tilde. The same thing as here, except that instead of doing just 1, I'm going to do sort of 1, 2, 3. Say that again. This? No, it's actually bj. So here I replaced b1 by b1 tilde because in the first dimension, the first Gram-Schmidt vector is the same as the first basis vector. Okay, I cannot do this in general. So b2 tilde is different from b2, right? b1 tilde is the same as b1. b2 tilde onwards, it's totally different. Okay, so I cannot do this in general.
And you're subtracting bj tilde components, so you should be subtracting bj tilde, and it'll turn out to be the same anyway, I think, because they're orthogonal.
Are you sure? Yeah. Thank you. Yes, so I got confused because of you. Thank you. Okay, so you get m orthogonal vectors. In fact, this process depends on the order of the vectors, right? So if I switch the order of b1 up to bm, I get a different orthogonalization. So how do I? So why is this useful? So you guys know more algebra than me, right? So I probably shouldn't be describing it in any case. Okay. All right. So I'm not going to do much else except sort of write it down in a slightly nicer way. Okay. In particular, I'm going to. So what this gives us is a way of writing down the basis b1 up to bm as a matrix times b1 tilde up to bm tilde. Right. So in fact, I'm going to call these numbers mu sub I comma j. Okay, it's the when I do the orthogonalization of I, so the multiple that I multiply with bj tilde is called muij. Okay, so just the notation. So what? Sorry. It's in fact b1 tilde up to bm tilde times 1, 0, 0, because b1 is equal to b1 tilde. Mu 2, 1, 1, because if I take b2 tilde minus mu 2, 1, b1 tilde, I get b2, right? And so on and so forth. So this is a sort of an upper triangular matrix with diagonal 1. Okay, this is because I just did a linear transformation to get from one basis to the other. Now this has an interesting consequence, which is that the determinant of B is equal to the determinant of B tilde times the determinant of this matrix. But what is the determinant of this matrix? It's 1, right? Because it's an upper triangular matrix with diagonal 1. Now what is the determinant of B tilde? So B tilde consists of a bunch of vectors which are all orthogonal, pairwise orthogonal, right? So the determinant of this matrix is in fact the product of the lengths of the tilde. I equals 1 to n. B tilde. Okay, so that's another way of writing the determinant of the lattice. It's a product of all Gram-Schmidt orthogonalized vectors. Okay, so that's that. So that's all very good. Now let's actually move on to the Lll algorithm. Okay. Okay. So first, let me sort of what are we trying to do, right? What is the intuition behind this algorithm? Right? So let's look at our favorite lattice again. And this is really a very sort of nice basis for this lattice, because it has short vectors, and this is a horrible basis for this lattice. Namely, can't even draw. Okay, this is a really terrible basis for the lattice. Why? Because it is long vectors. Okay. Let's notice another thing about these two bases. Okay. In this basis, the vectors are short and nice, and the angles between the vectors is actually close to orthogonal. Right? The angles are large. This basis has long vectors. It's a terrible basis, and the angle between the vectors is really tiny. Okay. In fact, this is not coincidental. Long bases with long vectors tend to have small angles between the vectors. Another way to think about it is that if you look at the Gram-Schmidt orthogonalization of this basis, you have this vector and the orthogonal component, right? And the orthogonal component is actually pretty large, right? I mean, it's almost the length of this vector. Why? Because the angle is large, essentially. If you look at the orthogonalization of this basis, okay, let me take this vector, right, and the orthogonal vector to the other vector, which is this vector. Okay, this guy is really, really tiny. Okay, and why is that the case? Because the angle between these two vectors is really small. So what I'm saying is that good bases with short vectors tend to have large angles between them and large Gram-Schmidt vectors. And bases with long vectors tend to have small Gram-Schmidt vectors. Okay, this is not entirely surprising, because again, you can write the determinant of the lattice as a product of the lengths of the Gram-Schmidt vectors. And if one of them is really small, so this is an invariant for any basis, right? I mean, the determinant of the lattice is the same no matter what basis you pick. So if there is a basis where one of the Gram-Schmidt vectors is really, really, really tiny, then it has to be compensated by other vectors, right? So the other Gram-Schmidt vectors are really large. And therefore, the basis has really large vectors. Okay? So our goal, it seems like, is to compute a basis with large, relatively large Gram-Schmidt orthogonalized vectors. Okay, that's the goal. That's what we should be doing to compute the short vectors. Compute a short basis and therefore short vector. Okay? And that is in fact the point of the Lll algorithm. What it does is it takes a basis, which is really terrible, it's like this basis, and computes another basis where the Gram-Schmidt vectors are large, and the basis vectors are more or less orthogonal to each other, therefore it's a good basis. Okay? So now, okay, so we have to, this is intuition, but we have to formalize it. And that's what LLM does. How do you formalize it? Let me keep this, let me keep everything. Okay, so Lll algorithm. This algorithm proceeds in 3 steps. Okay. One, we will define an LLL reduced basis. Okay, so this is a basis which satisfies some very nice properties, and we will show that the first vector in an LLL reduced basis has length at most 2 to the m-1/2 times lambda 1 of the lattice. Okay, it's the same number as in the theorem. Okay, so in other words, what this says is that if you can compute an LLL reduced basis, the first vector of this basis will be a relatively short vector. Okay. Well, what does that suggest? What should step 2 be? Compute an LLL reduced basis. Compute an LLL reduced basis given any basis of the lattice. Any basis in right. So this is the algorithmic part of the result, and 3, we analyze its running time and show that it's polynomial. Show that it's polynomial in the description length of the input, which is, I give you a basis. How many bits do I need to write down the basis? It's polynomial in that. Okay. So this is the outline of LLM. And now let's start. Okay. So what is an LLL reduced basis? Okay. Definition. A basis B is LLL reduced. Handwriting becomes worse and worse as time goes on. Reduced if it satisfies 2 conditions. So the first condition is that we'll let B1 tilde up to Bm tilde be the Gram-Schmidt orthogonalization. GSO is Gram-Schmidt orthogonalization. The first condition says that mu sub I comma j for every I and for every j less than I, the absolute value of mu sub ij is at most a half. Okay, so what does, remember, what is mu sub ij? Let's look at this basis, right? B1, B2, and so forth. What is B1 tilde? It is equal to B1. What is B2 tilde? It's this orthogonal component, right? And mu ij, mu to 1 in this case, is the multiple of B1 by which I shift B2. I shift B2 by a multiple of B1 to get B2 tilde, right? So what is the multiple of B1 by which I shift it? That is mu to 1. Okay, so that's from that from the equation over there. And what this condition says is that mu to 1 is at most a half. In other words, to get from here to here, I subtracted at most a half of B1. Okay. In other words, what this says is that the vector B2 lies in this nice interval, in this nice sort of vertical interval, right? So if B2 were actually here, then to get to the orthogonal component, I need to subtract a large multiple of B1. Okay? So if a basis satisfies this condition, it means that B2 lies somewhere here. It lies, between this vertical line and this vertical line, where the length of this is half. This is half B1, and this is half B1. Okay? So what does this say? It says that the angle, so if B2 were actually like here, the angle between B2 and B1 is really small. So what this condition says is that the angle between B2 and B1 is relatively large. Okay, so that's what this condition says. Almost. Okay, because there could be a B2 in this interval that lies between these two, but in fact the B2 could be here, right? So, I mean, it's not the case that the angle is large. The angle is in fact small. That's what the second condition takes care of. It says that for every I between 1 and n, the length of bi plus 1 tilde squared is at least delta minus mu I plus 1 I squared times the length of bi tilde. Okay, so let's parse this for a minute, right? So what this says in the two-dimensional case, so let's say I plus 1 is 2 and I is 1, right? So what this says is that the length of the second orthogonalized vector is large, is larger than a certain bound. Okay, so it cannot be that B2 is right here, because that means that the length of the second orthogonalized vector is pretty small. Okay, so that can't be the case. It says, what this condition says is that the length of B2 tilde is larger than a certain bound, which depends on B1 tilde. So B2 has to lie in between these two lines. That's what A says. What B says is that it has to lie above this line, above a certain line which depends on B1 tilde. So this is quite good. Okay, so if a B2 actually lies in this space, then truly its angle with B1 is large. It cannot be small. Okay, so think of vector here, vector here. It can never be small. Okay, so that's what we want to make sure. Okay, so that's the intuition. So
Could you give us what delta was?
yes, good. So the basis B is delta LL reduced. If this one. So delta is any number that you want. It makes sense if delta is in 0, 1, and in fact, what we will assume is delta equals something like a 3/4. Okay, so it's a small constant. Think of it as a constant between 0 and 1. Okay. Okay, good. So you can define this basis for any delta that you want. It may not make sense for some values of delta. You may not be able to compute it for some of the values of delta. But if you set delta to be 3/4, you can both compute it and it makes sense. So we'll see this in a moment. Okay. All right. Okay. So now what we want to Okay, so let's say, we saw what these two conditions mean geometrically, right? So what it means for, the angle between B1 and B2. Let's see what it means algebraically, okay, in terms of, these matrices.
Excuse me, can you
Yes.
tell me why the first condition concerns all ij pairs, but the second one,
Yes, it concerns only adjacent I and I plus 1.
so
It's
what's the difference?
Say that again.
So why the difference?
It's a very good question. I can, in fact, generalize this to, so the point is that if let me jump ahead, okay, a little bit. Say that what the algorithm does is it takes sort of adjacent vectors and it does a sort of a little sort of basis reduction algorithm on these two vectors and kind of, repeats this process. Okay, so all I'm concerned with in a single step of the algorithm is two vectors. And that I can actually do because, I only have to sort of deal with two vectors. It's not very complex and so forth. I can actually generalize this. So, this is not LLL, it's a generalization due to Schnorr. You can consider not just two adjacent vectors, but any set of k vectors. Okay, and then this won't be such a simple condition anymore. It'll be some more complicated condition on these k vectors, and that'll give you a better approximation algorithm. Okay, at the cost of a larger running time, because you're not looking at just these two vectors, processing these two vectors. You're looking at processing k vectors. Okay, so the bottom line is that you can generalize this to k vectors. It'll give you a better approximation algorithm, but a slower algorithm. Good. That's an excellent question, actually. Good. Okay, so this is what it means geometrically. What does it mean? What do these two conditions mean algebraically? Right? Okay, so we wrote B1 as B1 tilde up to Bm tilde, linearly shifted by a matrix, right? So I'm gonna sort of go ahead further. I'm gonna sort of normalize all these vectors. In fact, consider not B1, but B1 normalized by the length. So it's a unit vector in the direction of B1, right? And so forth over the length of Bm tilde. And that changes this matrix how? Well, this guy is going to be B1 tilde, this guy is going to be mu21 B1 tilde, and so forth. This guy is going to be B2 tilde, mu32 B2 tilde, and so forth. Okay? The first row got multiplied by B1 tilde, the second row got multiplied by B2 tilde, and so forth. Okay? And what the first condition says is that this matrix looks like B1 tilde. This guy is at most half B1 tilde. Right? In fact, the absolute value is at most half B1 tilde. Again, this guy is half B1 tilde, and so forth. And this is B2 tilde. This is at most half B2 tilde. And so forth. Okay, so that's what it looks like because of the first condition. Okay, because each mu ij is smaller than half. Absolute value is smaller than half. What does the second condition say about this matrix? Right? Let's rewrite the second condition a little bit. Okay, so what this says is B1 tilde square is at least mu delta minus mu I plus 1I square bi square. Bi tilde square. Okay, let's rewrite it as bi plus 1. So this is equivalent to saying that bi plus 1 tilde plus mu I plus 1 comma I bi tilde square is at least delta times bi tilde square. Okay, I didn't do much except, took this term with the mu I plus 1I to the left hand side And because bi plus 1 tilde and bi tilde are orthogonal, I can actually write it down as a sum, square of the sum, as opposed to the sum of the squares. And then what is left is delta. Okay, so this is another equivalent way of writing this condition. Why does it matter? Well, let's look at a little submatrix of this guy, which is bi tilde, right? Mu I plus 1 I bi tilde, bi plus 1 tilde. Right? So this little 2 by 2 submatrix of this big matrix. And what this condition says is the following. The length of this column, which is mu I plus 1 bi tilde square plus bi plus 1 tilde square, this guy, is at least delta times the length of this column. Okay, so let you stare at it for a minute. Okay, so these two conditions, they say that the matrix is of this form with at most half, entries, and the second condition says something about a little 2 by 2 submatrix of this bigger matrix. It says that the right hand column is at least as long as the left hand column. Why does it matter? We will see in a minute. Okay, so that's the magic of LLM. Okay, so this is what it means algebraically. So why does it? Okay, so first let's prove that if a basis is LL reduced, then it has the first vector in the basis is relatively short. Okay, so that is the step one of this process. Okay, so how do I? If delta is smaller than 1 over 4, it doesn't make sense. So delta has to be larger than 1 over 4. Yes, it's because of this, right? So let me just say that it's a good question about delta. So delta, think of it as a quarter. It's between a quarter and 1. The closer it gets to 1, the slower the algorithm performs. The closer it gets to a quarter, it becomes meaningless. This notion becomes meaningless. Because at some point there is a delta minus 1 over 4 term that comes in the denominator. So unless you have a way to divide by 0, so yeah, it's an open integer. You'll see this in a minute in the analysis. Okay, so the first thing we want to show is that an LL reduced basis has a very short vector. Okay, so that's the first order of business. How do I? Okay, so let me erase this. So, claim let B be delta LL reduced, then the length of B1 is at most 2 over root of 4 delta minus 1. There you go. To the m times lambda 1 over. Okay, so delta is smaller than a quarter, you're in trouble. Okay, it's at most a quarter. So if we set, remark, if you set delta to be a 3/4, for example, you get a vector which is at most 2 times m minus 1. 2 to the power m minus 1 over 2 times lambda 1 over, as promised. Okay, so so this gives you an exponential approximation. Okay, you can set the delta to be a little bit larger, a little bit smaller. It doesn't matter. I mean, it changes the quality of the approximation, but not very much. Okay, so how do we show this? Well, okay. So remember that this condition says that bi plus 1 tilde is at least delta minus a quarter times bi tilde square, right? Because all the mu's are smaller than a quarter. Okay. So in other words, bm tilde square is at least delta minus a quarter bm plus 1 tilde square, and so on and so forth, until I get to delta minus a quarter to the m minus 1 b1 tilde. Okay, and b1 tilde is equal to b1, so this is delta minus a quarter m minus 1 length of b1. Okay, so this is just straight from the definition of an Lll reduced basis. So something I forgot. So I'll use okay. So I'll use a fact which I'll show in a minute, which is that lambda 1 of L, which is a lower bound on lambda 1 of L, which says that it's at least for every basis B. If you look at the minimum Gram-Schmidt orthogonalized vector, the shortest vector is going to be at least as long as this. Okay, I'll prove this in just a minute. But once you have this, what do we get? So from this, we get that bm tilde the length of b1 is at most delta minus a quarter to the I minus 1 length of bi tilde. Right, so this is essentially reversing this series of inequalities. I didn't do much, which is at most delta minus a quarter to the m minus 1 over 2 bi tilde. Right, so why is this the case? This is because delta minus a quarter is smaller than 1, right? Delta is in the interval 1 quarter 1. So this number is smaller than 1, so it's okay to sort of increase the numerator. That only makes the inequality less tight. Okay? So this is like saying, half to the 5 bi tilde is at most half to the wait, something wrong here.
There's a minus missing in the exponent.
There is a minus missing in the exponent. So, thank you. Minus I minus 1 over 2. This is minus I minus 1 over 2. Now this makes sense. Okay. Good. Okay. So now B1, the length of B1 is at most this factor times the length of bi tilde for all i's. Right? So in particular, the length of B1 is at most delta minus a quarter to the minus m minus 1 over 2 times the min I bi tilde. Right? It holds for all bi tildes, therefore it holds for the minimum of the bi tildes. And now we use this little sort of fact which I didn't prove to you yet, that this is at most delta minus a quarter to the minus m minus 1 over 2 lambda 1 of n. Okay, and that's that. We're more or less done. It's just a matter of rewriting. So this is 2 over root of 4 delta minus 1 to the m minus 1 lambda 1. Just rewrite the same expression to get this. Okay, so all I need to show now is this little inequality, which gives you a sort of a lower bound on the length of on the shortest vector of the lines. Okay, so let's do that actually. What should I raise? Huge dilemma. So I'm assuming that you guys have GS Gram-Schmidt business in your mind. Okay. So this is what we're going to show. Proof. Okay. In fact, we will show that for every lattice vector, call it b times x, right? So take any lattice vector, b times an integer vector. We will show that the length of this vector is at least min of the length of the Gram-Schmidt vectors. Okay, this is what we'll show. We will show this. How does this work? Okay. So let's write x b times x. There's no tilde. Right, so let's write x as x1 up to x sub m, and let j be the largest index such that x sub j is not equal to 0. Okay, so could be that the vector x has a whole bunch of zeros at the end. Forget about them. Pick the largest index, which is non-zero. Okay, you'll see why in a minute. Let's compute the inner product of bx with bj tilde. Okay, the inner product of the Gram-Schmidt vector with this lattice vector. So this is simply the sum of xi bi with bj tilde, absolute value, right? So this is, so if I take the inner product of bj tilde with any of the bi's here, the inner product is going to be 0, which is not quite. Yes. Okay. Good. So a whole bunch of these xi's are 0, right? In fact, all the xi's where I is larger than this j are 0. And for all the other xi's, the inner product of bi with bj tilde is 0, right? Because the inner product of bm with any sort of smaller, with any vector b1 up to bm minus 1 is 0. So in fact, this turns out to be the length, the modulus of the absolute value of xj times the inner product of bj and bj tilde. Okay, and this is in fact xj times the length of bj tilde squared. You see why this is the case, right? So if I take the inner product of bj tilde with any of the bi's, where I is smaller than j, I get 0, but because it's all orthogonal to these vectors. The only thing that survives is the inner product of bj with bj tilde. The other ones, bi for which I is bigger than j, they don't matter anyway because the xi's are 0. Right? So you get this. Now,